Hi everyone, welcome to AI Exact channel. This is Akash Gangwar and today we'll be studying straight lines lecture 2. So basically we'll be discussing about few basic concepts like centroid, incenter, circumcenter and a few other concepts. So let us start the discussion with centroid. Centroid of a triangle is a point of intersection of its medians and centroid divides the median in 2:1 ratio. So this is the most important point which you have to remember. Now the coordinates of centroid are x1, x2, x1 plus x2 plus x3 divided by 3, y1 plus y2 plus y3 divided by 3. And x1, x2, x3 and y1, y2, y3 are the coordinates of the vertices. So let's see how we derive this particular formula. So let's say we have this triangle A, B, C. And this one has coordinates x1, y1. This one has x2, y2. And this one has x3, y3. Now we know that a median drawn from the vertex to the opposite side divides the opposite side in the ratio 1:1. So basically it equally divides the opposite side, right? Now this ratio is 1:1. So basically with the help of midpoint theorem, let's say this point is D. So this point would be x2 plus x3 by 2 and y2 plus y3 by 2. These are the coordinates of this point. Now again, if I have to find out the point G, so we call centroid as G. If I want to find out the coordinates of point G, now we know that the centroid divides the median in the ratio 2:1. So this is 2 and this is 1. So now you can use the section formula to find out the coordinates of G. Let's say this is x and this is y. So now you'll have to use that mx1 plus nx2 divided by m plus n. And similarly for y, you'll have to do that my1 plus ny2 divided by m plus n. So if we use that formula, then we'll get these values x1 plus x2 plus x3 divided by 3 and y1 plus y2 plus y3 divided by 3 as the coordinates of centroid. Now let's talk about incenter. The incenter of a triangle is a point of intersection of internal bisector of angles. So let's say this is our triangle A, B, and C. So basically this line, this internal angle bisector is dividing this angle into equal parts, right? Now let's name it as C, let's name it as B, let's name it as A. So this is the standard convention that against the vertex C, we name the side as small c. Against the vertex A, we name the side as small a. And against the vertex B, we name the side as small b. This is the standard convention. You have to use that. Now, in the angle bisector theorem says that the angle bisector from a vertex to the opposite side divides the opposite side in a ratio that is equals to the ratio of the sides containing the angle. Like, so this is the angle and sides containing the angle is C and B. So basically this is Cx and this is Bx. So this side is being divided by the angle bisector in the ratio C is to B. Okay. So x is some constant. So Cx and Bx. So this Cx plus Bx equals to A. So this is how this line being divided. Now, with the help of section formula, you can find out the coordinates of this point. Let's say these are the coordinates x and y. Let's say this is x1, y1. Let's say this is x2, y2, and this is x3, y3. So with the help of section formula, you can find out the coordinates of x and y, right? Now again, let me draw one more angle bisector of this particular angle C, right? Now, if I talk about triangle A, and let's say this point is D. If we talk about triangle ADC, now this angle bisector is also the angle bisector of triangle ADC, right? Because this angle is being divided. Now we know that this bx is nothing but actually this is b upon b plus c multiplied by a. If I try to find out the value of x, then I'll get this value only. So basically this length, sorry, CD length is b upon b plus c divided into a, right? CD length, this length, and this length is b. So we know the ratio of AC is to CD, right? We know the ratio of AC is to CD. And since we know the ratio of AC is to CD, we also know the ratio of, let's say this point is E, AE divided by ED with the help of angle bisector theorem. If AC is to CD is this upon B. So if AC is to CD, if is B upon BA divide by B plus C. Then AE also, AE divided by ED is also the same, right? Let me reiterate it once to avoid the confusion. So what we did, we found out the x and y with the help of section formula, because we know the coordinates of B and C, and we know that with the help of angle bisector theorem, we know that if this ratio, if these sides are C and B, then BD is to DC is also C is to B. So now we know the ratio C is to B, and we know the coordinates. So basically, with the help of section formula, we can find out the coordinates of x and y. Now we know the length DC with the help of simple ratio and proportion. We know the length of CD, and we also know the length of AC, that is B. So basically we know the ratio AB divided by CD. And since we know the ratio of AC is to DC, we also know the ratio of AE equals AE is to DC, because of the angle bisector theorem. Now we know this ratio A is to CD, A is to ED, and we know the coordinates of A, we know the coordinates of D. So basically we can find out the coordinates of E. So that comes out to be, so it's a little complicated process, but it's very conceptual to understand, right? So you have to remember this formula as well. Now let us talk about orthocenter. It is the point of intersection of altitudes of a triangle. So let's say we have this, sorry. Let's say we have this triangle A, B, and C. Now if I drop a perpendicular from here, if I drop a perpendicular from here, and if I drop a perpendicular from, from here, then this point is called as orthocenter. Okay. Now, one thing to understand is, when I am denoting centroid, I am denoting with the help of G. If I'm denoting incenter, then I'm denoting with the help of I. And if I'm denoting orthocenter, then I'm denoting with the help of O. Now, let's talk about the last point, that is circumcenter. It is the point of intersection of perpendicular bisectors of a triangle. So let's say we have this triangle A, B, and C. So we have to draw the perpendicular bisector of every side. So this is the perpendicular bisector. This is dividing this into equal parts. Similarly, over here, this is the perpendicular bisector. So this is 90 degree. This is also 90 degree, and this is equal. And sorry, this is also perpendicular bisector, and these two are equal. So this point is called as circumcenter, that is being denoted by C. Now here are some important points which you should be remembering. In right angle triangle, orthocenter is at the vertex with 90 degree, and circumcenter is the midpoint of hypotenuse. Let's try to see what does this mean. Let's say we have this triangle, which is right angle triangle basically. Let's say this is A, this is B, and this is C. Now in case of orthocenter, what we do, we try to drop perpendiculars from every vertex, right? So from A, we are dropping perpendicular, and since this is 90 degree already, so this would come out over here only. Similarly, from C, if I'm dropping perpendicular, it would come out over here only. So basically, orthocenter of a right angle triangle is nothing but the vertex with the angle 90 degree. Now, we all know this property, that the diameter subtends right angle on the circle, right? We all know this property from 9th and 10th class. And we also know that the center of diameter is nothing but circumcenter, right? So if I take this right angle, then we know that this particular point, this is hypotenuse, diameter is nothing but hypotenuse, and this particular center point is the circumcenter. So similarly, in this right angle, we can say that the midpoint is circumcenter of ABC triangle, right angle triangle. Okay. Now the second property says orthocenter, centroid, and circumcenter are always collinear, and centroid divides the line joining orthocenter and circumcenter in the ratio 2:1. Now centroid has a very good relation with 2:1 ratio, and that is also very useful. So we also we studied that in case of a triangle, if I'm drawing a median, then centroid divides the median in the ratio 2:1. Similarly, we also know that it's a fact that orthocenter, centroid, and circumcenter, these three are collinear always, and centroid divides the line joining O and C in the ratio 2:1. So 2:1 is a very special point for centroid. Now, in case of isosceles triangle, G, O, I, and C lie on the same line, and in an equilateral triangle, all these four points are same. So let's draw one isosceles triangle. So these two sides are actually equal. Now, when I try to draw a perpendicular bisector, sorry, an angle bisector, this would eventually be the perpendicular bisector as well because of the symmetry, right? This would also be the median because it's a perpendicular bisector, so it's also median. And since it's a perpendicular, so it also satisfies the condition of orthocenter. We are talking one perpendicular. So it's a perpendicular bisector, median, and angle bisector as well. So basically, we also know that all these points lie on these lines only, this particular line only. So in case of isosceles triangle, G, O, I, and C lie on the same line. Basically, all are collinear in case of isosceles triangle. Now, in case of equilateral triangle, all points are same because of the extreme symmetry. Everything is symmetrical. So all these points are exactly same. Now let's look at one question. The incenter of the triangle with vertices 1, root 3, 0, 0, and 2, 0 is. Now, the first thought should be, in normal case, if you know the formula, the first thought should be to find out the values of A, B, and C, and then you can utilize the formula for incenter to find out the value of the incenter coordinates, right? But that shouldn't be the approach actually, because that would be too lengthy to do it. So let's try to plot the points first. So whenever we get certain kind of such kind of cases, try to plot the points first. So 0, 0 is over here, 2, 0 is over here. And as soon as I see 1, I can see the symmetry because 1 is the center. So basically it's in this somewhere over here, 1, root 3. Now if I try to check the distances between these points, I'll see that this distance is 2, this distance is also 2, and this distance is also 2. So basically it's an equilateral triangle. And in case of equilateral triangle, we know that every point is same. It's either it's orthocenter, it's circumcenter, or incenter, or centroid. All points are same. So the easiest calculation is therefore centroid. In case of equilateral triangle, centroid is also same as incenter. So x would be 1 plus 0 plus 2 divided by 3, and y would be root 3 plus 0 plus 0 by 3. So basically that comes out to be 1, and that comes out to be 1 by root 3. So D is the correct answer. Now let's look at this question. The x coordinate of the incenter of triangle that has coordinates of midpoints of its sides as 0, 1, 1, 1, and 1, 0 is. Now again, I can see some kind of symmetry over here. Let's see. So we have 1, 1 over here. This is 1, 1. And we have 1, 0. This is 1, 0. And we have 0, 1 over here. Now I can see that this line is horizontal, perfectly horizontal. This line is perfectly vertical. Basically, this is 90 degree and this is 90 degree because this line is horizontal, right? Now we know that in a triangle with the help of midpoint theorem, if this is the midpoint, if this is the midpoint, if I try to join this one, so this becomes parallel to this base, right? So basically, if I try to join every midpoint, if I try to join these two midpoints, then this becomes parallel to this one. So similarly, over here, these all are the midpoints. So now the line joining this point and this point is horizontal, exactly horizontal. So the base should be along x-axis only because it's also passing through this point. The base is passing through this point. It's also parallel to this particular line. So basically it should be along the x-axis, right? Similarly, this second side should be along the y-axis. Now the interesting thing over here is we know that if these two lines are intersecting, if these two sides are intersecting, then this should be one side of the triangle. Why? Because if this particular line, if this particular side is parallel to this midpoint line, and if this particular line is parallel to midpoint line, then this is the only possibility where they can intersect. They cannot intersect anywhere because they have to pass through these points as well. If suppose I'm trying to draw something of this sort, then it won't be parallel to this line, won't be parallel to this particular line, midpoint line, right? So this is the only possible case that this is one of the points of one of the vertex of the actual triangle. Now since you have got this, and we know that midpoint line, line joining the midpoints is half the length of the base, which is to which it's parallel. So if this length is 1, so this length should be 2. So this would give me 2, 0 as 1 point. And similarly over here, I'll get 1 point called 0, 2. Now we have got the points. of the triangle 0, 2, 0, 0, and 2, 0. So this is the triangle, right? So basically, we have to find out the coordinates of the incenter of the triangle that has coordinates of midpoints of these points. So we have got the points, we have got the distances. So this length is 2, this length is 2, this length is 2 root 2, right? Now you have got the lengths. Now you have to apply the formula of incenter and you will get the answer. Now let us talk about introduction of locus. So basically, locus of a moving point is the path of the point which satisfies some geometrical conditions. So the best example to understand locus is circle, right? So let's say I have a nail stuck in the ground over here, and I have tried to, attach one rope to it, and this rope goes like this. Now there's a pen or pencil, you can say, over here, and I'm trying to move it around it. So without changing the distance, basically I'm stretching this particular rope, basically making it taut, and I'm moving the circle, moving this pen around it. So that would basically make a circle because this distance is constant. This distance is constant and this pen is moving. So that would draw a circle, right? Now, this is the geometrical condition which we are talking about in the definition. So geometrical condition is your distance from the center is not changing. Distance is constant, but this point is free to move. This point is free to move, but with this kind of condition that this distance is not changing. So it can move in this trajectory only. So this trajectory is called as locus. Okay, so that is the best example. One more example you can take. Let's say we have a ladder over here, and if I try to observe one point which is at the center of the ladder, and ladder is trying to fall, so ladder is falling, but the condition is ladder is not losing touch with any of the walls, neither from the floor and nor from the walls, so it's not losing its touch. So this is one snapshot of the ladder which is following. Now let's make one more scene scenario. So now it has fallen down a bit, and this is the center now. Now let's make one more scenario. Now the point is over here and it has fallen a little bit more. Now you can see that the trajectory of this point is somewhere like this. So this is the locus of that center point when the ladder is falling without losing the touch from the ground as well as from the wall. So methods to find the locus. The step one is draw a rough sketch showing the conditions given and mark the moving point as PHK. So HK is just the convention. You can mark it as A or B, or you can mark it as anything else, but we tend to use the convention HK. Now you can apply the restrictions conditions on the point P to get the relation between H and K, and replace HK with the XY to get the final equation locus. So these are the steps. These are the theoretical steps. You'll get to understand more about locus when we see the examples. So let's meet tomorrow for the next lecture and we'll see the examples of locus over there. And thanks for watching.